The last two sections, we learned how to triangularize any arbitrary linear system that we're trying to solve. We're not quite done with getting the solution, however, because we now need to entertain one last algorithm, and that is called back substitution. Secondly, after we're done with that, and we've got ourselves a solution, we are going to learn how to measure any error associated with our algorithm. So with that, let's go back to our 4x4 example and solve this upper triangular system. We did a lot of work to create it, so it's time for us to come up with a solution vector that uses that. Here is the revised matrix A. It's been triangularized. Our solution vector x has not been impacted because the row reductions we've done do not impact the solution, but our b vector has been impacted through the triangularization. If we multiply a times x, but just focus on the last row of a, the operation would be 0 times x1 plus 0 times x2 plus 0 times x3 minus 3 times x4 is equal to minus 3. That looks like a simple equation to solve. Here I've reproduced it, and it's very obvious that the only thing that survives the zero coefficients is the very last variable, x4. Well, this very simply can be solved as x4 equals 1. You know, the other thing that's kind of nice about this is if we generalize this 4x4 matrix to any size at all, the same thing happens. We're going to have a run of zero coefficients for all indices up to the very last x. And we still have just as simple of a solution with an n by n matrix as we did with a 4x4. Well, that makes me think that x3 on this 4x4 system might be just as easy, because now that I have x4, why couldn't I plug this 1 that I've already solved right into the solution vector, and from that try to evaluate x3 using the third row? Well, let's go ahead and try that. 0 times x1 plus 0 times x2 plus 2 times x3 minus 5 times 1. I still have one equation and one unknown because I'm going to set that all equal to minus 9. Well, that's pretty easily solved by just adding 5 to both sides of this equation, which we've done here, and you can very readily calculate the result to be minus 2. So let's go ahead and look again at my more general case. If I had a full n by n system rather than just 4x4, the exact same simple formula still applies. I take the second to last b coefficient, which was minus 9 on the 4x4, and I just subtract off the coefficient applicable to x sub n, which is going to be this minus 5 right here, and I divide by the third, or the row 3, column 3 entry in this term at the bottom. And so the generalization looks exactly for an n by n as it does for a 4x4 or a 5x5 or anything else. I should probably focus now on the second row and plug in the results that I've already gotten for x4 and x3. So I end up with 0 times x1 minus 4 times x2 plus an inner product of constants. You know, I have a growing solution vector that I'm taking the inner product of whatever is appropriate on that particular row, and it's really just coming up with a number that I could then add to the other side of the equation, which is going to be a b of minus 6, and then I solve again for x2. Or in more general forms, what you're seeing here is the inner product of already solved variables is just growing. And so you have to keep track of that. So if we just keep that going, we end up with 6 times x1 plus an inner product of coefficients times known solution values that just produces a number that we set now equal to 16. and we end up having one equation and one unknown. Here is the formula for the 4x4 system, and here's how you would generalize that to an n by n system. This was our first step. We take the last outcome variable, the last b, and divide it by the lower right-hand corner of our triangularized matrix. That gives us the last solution. And then we have to do a for loop. The for loop is kind of implied by this where statement. And I start increasing my sum. I start summing up all of those values that are already known times their respective coefficients applicable to row I, and I do the subtraction, and that becomes the ith variable, which then adds to this growing list of solved variables. Notice how we have to do it backwards. So if you imagine this to be a for loop, I am saying for I equals n minus 1 all the way down to 1, do this expression here. Well, let's write it in that form. So this becomes now the actual pseudocode associated with this back substitution process. This was the first step that we talked about at the beginning. Now we need to set up our for loop to march through the remaining rows. We start on the second to last row. Why second to last? Well, we've already solved the last one with this very first statement. So we start with the second to last row and we march down, or maybe march upwards to the first row. What do I want to do? Well, I want to be creating an accumulation of values that will then end up being divided by the appropriate diagonal element. It starts with the appropriate b value. So I'm on row n minus 1. If we just start this thing from the top, I let n equals n minus 1. Well, I'm using b sub n minus 1 because that's what I is on the very first pass. I overwrite a brand new variable called sum. Then I am going to set up a second inner loop which starts with 1 greater than the row number and goes all the way out to n. Well, what that's doing is picking off within the row the appropriate a coefficients that match with the already solved values of x. Well, on the very first pass, when n was equal to minus 1, I only had one such solved variable, and that was x sub n. But that looks like it's working pretty nicely here in this for loop, because on the very first loop of I is equal to n minus 1. If you take n minus 1 plus 1, you get n back. So that means on the very first pass, our j is going from n to n. Well, that means it's a one-pass loop, and it will pick up x sub j, which is n. So it's picking up our only known value, multiplying by the appropriate a coefficient, and subtracting that off the sum, which at this point is just the b value, the appropriate b value. Since this at the beginning is just a one-pass loop, we're done. We do the division on the second to last row and second to last column, which was appropriate for the algorithm, and I just got x sub n minus 1. I come back around on this loop again. I is now n minus 2, so I start off with b n minus 2. That's appropriate, but this loop will be a two-pass loop. Since I is n minus 2, if I add 1 to it, we start off with j equal to n minus 1. This goes from n minus 1 to n, which means this loop will happen twice. Well, that's appropriate because we currently have in our solution vector both x sub n and x sub n minus 1 solved. So we're subtracting these off one at a time using their appropriate a coefficients, and we end up getting the right sum value that is ready for division by the appropriate diagonal element, and the algorithm is working just great. And that's the whole thing. So it's really very compact. You can do this back substitution very efficiently, very few floating point operations, and you will get a complete solution vector. I do want to talk about that second topic called error. We have calculated a solution vector. Now, we haven't calculated just some number. We have calculated an entire vector of numbers. After all, we're solving a linear system of equations. So the question is, how good is it? Is x1 really close and x2 really far off, or are they all really close to the right answer? What is the really right answer? These are questions that we really need to address. And we'll do that using what we call errors and residuals. The absolute error is simply the calculated result minus some unknown truth. Now that sounds a little bit unnerving. If it's unknown, how am I going to be able to calculate this error? And the answer is you aren't. You can't calculate it. It's a theoretic value, but we have to pay attention to it. We're going to give now our calculated solution vector a name. We'll call it x tilde. So everything we just did on the previous slides resulted in x tilde, not really x. X is going to represent the exact but unknown true answer. And therefore, we have some difference between the calculated result and the unknown truth, which we will call error vector E. Rather remarkably, we can do a lot with it if we take a look a little differently at how we're going to view error. We're going to introduce a concept called a residual. Let's suppose we take our known matrix A and multiply it by this unknown error vector. Well, what does our matrix algebra allow us to do? We can substitute E for what it is, x tilde, the calculated result minus the truth, and we can distribute A through that difference and look at each piece separately. Well, x tilde is known and A is known, so I can do that multiplication. A is known, but x isn't known. However, I'm solving the equation ax equals b. That was the going in position, which means I can replace ax with the vector b, which is known. So that means by simply pre-multiplying this unknown error vector E by my original matrix, I come up with an expression that's useful and I can calculate, and we will call that the residual vector. Let's just write down the definition. This is how we're defining the residual. The dimension of R will be the same as the dimension of the solution, and it could be 1,000 values. That doesn't really help us much. But what we could do is look at its inner product and take the square root of it, which turns out to be a very standard distance norm. We're building ourselves an n-dimensional ball and asking what the radius of that ball is, and we're calling that the 2 norm, and we use these double bars here to represent that norm. What I want you to do is go back to the P code that we just reviewed, and I want you to turn that into a MATLAB program. I'm going to email you an Excel file that has 2 tabs. It's got a tab called A and a tab called B. Well, A contains a matrix of interest and B contains an outcome vector. I want you to load that from the Excel file into MATLAB. I'm also going to give you code to do that in case you don't know how to do that. And I want you to triangularize that matrix A in place. This item C here might be a little confusing the way it's written. It looks like I want you to augment B onto matrix A. That's not what I mean. I want you to take the B vector that we would normally augment and keep it as it is, as you load it. Your algorithm that we described doesn't require you to join B with A, and I don't want you to do that. After you've done the triangularization, find out if matrix A is full rank. Use your own code to do that. You're going to have to create it. It's not in the notes, so you have to think about that a little bit. And you may not use trace, you may not use rank or any other MATLAB function to accomplish that. Then as the next step, use the back substitution we just covered and create the solution vector X. If you do print out the results, it's easier to debug. But the way I grade it is I load your code and I compare it to mine and see if we got the same answer. I do score you on a few other things. I want you to set up an integer counter that counts the number of additions, subtractions, multiplications, and divisions that you do, otherwise known as flops or floating point operations. Also, Your neatness matters. I expect good indenting. Every single line should have a comment associated with it, even if it's just 2 or 3 words to tell me what you did. So with that, I think that covers it. We have now completed section 2.1 in its entirety, and next time we're going to go on to some new improvements of solving linear systems in section 2.2.